Everyone, thank you for being a part of our class today. And if you have not subscribed, I want to encourage you to do that. And then you can also comment and share and like. Today, we are looking at a question on the board. The question said that air at 1 bar and 298 Kelvin is compressed to 4 bar and 298 Kelvin by a mechanically reversible process. Calculate the quantity of heat work required, change in internal energy, and change in enthalpy of the system if the air is subjected to cooling at constant pressure, followed by heating at constant volume. We have the specific heat capacity of air at constant volume to be 20.78 joule per mole per Kelvin, and then the specific heat capacity of air at constant pressure to be 29.10 joule per mole per Kelvin, and then molar volume of air at 298 Kelvin and 1 bar is equal to 0.02479 meter cube per mole. So here, based on that, we are going to look at how we're going to work on this. If you look at it very final, that there's a two process that happens simultaneously, that happen after the other. The first one we have there is the cooling aspect of it. So without wasting much time, let's see how far we can go in tackling the problem with the limited time we have. So here we have in the first process involve what? Cooling when the temperature from the cooling when the pressure is constant. So the cooling now starts from we said that at 1 bar and 298 Kelvin. So the first thing we do here to get the work done is to find the volume of the final volume of the process during the cooling. We find the final volume. So to get the final volume, we can use the Boyle's law. So using the Boyle's law now, we know that the initial volume here, our first volume at the 1 bar is 0.0247, and then the pressure at that point, the pressure we have at that point is 1 bar. Then being that the thing is in a confinement that has a volume of that can sustain a pressure of 5 bar, and the idea here is that the thing is movable, the piston in it has a kind of cylinder and a piston that can move at will without any resistance, just like what we have in explanation of Boyle's law. So in this case now we have the volume. The volume we're looking for is what we don't know, but the pressure at that point is believed to be, according to the question here, is 4 bar. It's 4 bar. Sorry, let me get 5. It's 4 bar. So now when we make V the subject of the formula, we'll find out that 0.02449 divided by times 1 divided by 4. That is what we'll have. It will give us equal to 0.00619.925 meter cube. This is what we have as our volume. So this volume now is the final volume at the cooling process, during the cooling process on constant pressure. This is the volume. Then the next thing we are going to do here is to find the temperature. the temperature in the first process. In the first process, we find out the temperature of the cooling, the final temperature of the cooling. Where do I put this in now? Okay, let me clean up. So to find the temperature at the first stage, say that the cooling, that's it was suggested towards cooling at constant pressure. So we have volume 1 and T1 equal to V2 over what? T2. This more like Charles law. So the volume here, the V1 is equal to 0.024449 all over the initial temperature, which is 298, equal to the volume, the final volume. The final volume we have 0.061925 all over T. So at this volume, the temperature is believed to be T2. So now making the T to the subject of the formula, making the T2 the subject of the formula, we'll find out that T2 is equal to this over, for that we have times 0.001925 all over 0.02479. That will give us, we have 74.5 Kelvin. This is the temperature, the final temperature of the cooling within that confinement. So now with this information we have, the next thing we're going to find out here, we know that, remember that specific heat capacity at constant pressure is equal to change in enthalpy over change what in temperature. So using this, that means enthalpy in this first process is then equal to change in specific heat capacity under constant pressure multiply change in temperature, which is also equal to what? Quantity of heat. So with this at stake, having this information, and the next thing we'll do is to go into work and clean this thing. Okay. Alright, let's continue. So we have our final temperature and we need to get the quantity of heat. Here we have quantity of heat is equal to, like what I've already stated before, we have already done that. So now we have to substitute. Substituting here, we have our specific heat capacity at constant pressure. At constant pressure to be 29 bracket changing temperature. We have this is our final temperature. This is our final temperature minus our initial temperature, which is 298 Kelvin. So when we subtract, what we have here should be minus 223.5 multiplied by that means the specific heat capacity here. Specific heat capacity here will then be, if we multiply it, to have 6 minus 6,503.85 joule. That's the quantity of heat that we have at the first state. So the next one we're going to do here, and we also know, we know that we know that um, quantity of heat can also be equal to, I think this one is a bit better now. We have it to be a change in enthalpy. This is the pressure and the change in volume. When we subtract that, we have this to be 1/8 1/8 should be 1/8 bracket minus. So so bracket minus, we have it to be 0 points plus. So by adding up this thing, by adding up together, we have equal to 44644 joule. 4644 joules. That is the another quantity of energy that we have there. This is the one that occur in the system, and this second one is also another this one quantity of energy that occur between the enthalpy and the work done in the system. So this for the work done in the system, and then during the second phase, when we work on the second phase, at the second phase we find out that the second phase, the second process, the volume now is constant. We have constant volume, and the change in internal energy during the process is equal to, like we all know that volume will give us change in heat capacity at constant volume is equal to V over change in time. So if we cross multiply, it will give us over change in time. So our specific heat capacity at constant volume, which is something as 20.78, and change in temperature. This time the temperature, since it's been heating, the heating is going on, the heating process is going on. What we have there is that the temperature is now going up again within the confinement from here to from initial temperature of this where it was during the cooling process. So in this case now, when we subtract it, if we subtract, we will have bracket 3.5 I'm sorry 5 multiplying through, we have 4644 joules. 4464 joules. So in the complete process, since we have done the second, we're able to find out the quantity, the change in internal energy in the second process. Now to the complete process, now the total energy, quantity of energy we have in the complete process is then 6503.85 plus plus 4644 joules. This one is minus, negative, equal to. So by adding them together, we have minus 1859.85 joule. That's the total quantity of energy in the system. Now the total internal energy in the system, the total internal energy of the system will have it to be total internal energy. You can put T there. Total internal energy of the system we have it to be minus 4644 joule plus 4644 joule 2. Then everything will give us 0 joule. So now we'll talk about the work done according to the first law of thermodynamics. We have it to be change in internal energy is quantity plus work done, and we have our internal energy to be 0. Internal energy, now let's just quickly rush it like this. Internal energy is 0, and then we have our quantity of heat, or perhaps just move it to the other end, we have it to be equal to this. So the work done now is total work done, we have it to be changing minus this. So our change in internal energy is 0 minus quantity of heat. The total quantity of heat here we have it 18.5 points. So this multiplied, it means that work done is 1859.585 joules. That is what we have here. Thank you so much for staying with us today, and I wish you subscribe. I want you to subscribe, like, and also share.